Hi everyone, thanks for joining. So my name is Pierre-Yves. I'm just as Bruno said, I'm CTO and co-founder at Exoscale. We're a cloud service provider. I'll spare just two words on what you will do, and I indeed enjoyed working on distributed systems as well as the monitoring and the observability ecosystem quite a bit. Have an extensive open source, almost open source past, if I were to be completely honest, in both of these fields. And today I'm here to talk mostly about orchestration and how we tackle it at Exoscale and what part Clojure plays in this. We don't build all of it in Clojure, but I'll only be talking about the bits that we do in Clojure. I have just an extremely small digression around the areas where we don't use Clojure at one point in the presentation. So yeah, we do infrastructure as a service. We fight the three big names. So we made the extremely poor choice of choosing Microsoft, Amazon, and Google as our main competitors. In retrospect, not the smartest of ideas. That being said, we are now edging, our comfortable space as a good European alternative to the big ones, with zones mostly in the German-speaking part of Europe. And that's what we do. That's what infrastructure as a service looks like, at least in our part of the world. Most of our customers tend to use us through automation tooling. So infrastructure is not necessarily where people think of Clojure first, right? And especially infrastructure as a service provider, because after all, in many people's head, it only involves installing OpenStack and buying lots of expensive hardware. So we did the former. We bought a lot of expensive hardware at Exoscale that has our own, but we also do a huge amount of software development. In the intro chat, I was describing a bit the split between in the engineering team. So yeah, half of the engineering team spends the vast majority of their time developing software. The software we develop ranges, so we almost rely exclusively on our internal intellectual property, as well as a couple of key open source projects as well. But today I'll be mostly talking about orchestrators, which is the part in red. So we orchestrate many things and have different software stack to orchestrate different parts of the product lines we have, such as our managed Kubernetes offering, load balancers, and VM instances. So before I get into that, I'll just spare a handful of words about what it means, for instance, to deploy an instance. Say you want to create a new virtual machine instance. What does this entail? Because if you've ever done it locally with libvirt or VMware, I mean, you probably have a notion of what this entails. But what does it entail for a provider? And purely from the infrastructure standpoint, I won't be detailing what we do for how we actually look at what you consume to ensure that there's a billing statement at the end or things like this. But purely from an infrastructure perspective, there's a network and storage component, as well as a compute one, which deals with placement. And something that intuitively can feel a bit simple ends up being already a sort of a maze just for this small task of deploying a new instance. So, from the API call we get, we need to figure out which public IP you're going to get, and then figure out which hypervisor you're going to land on, which needs to honor a certain amount of placement constraints. Potentially, you have anti-affinity groups, which mandate that you shouldn't be collocated with other instances. Maybe you choose a specific how would I say, hardware family for the instance you want to deploy. So that has to be taken into account in that allocation decision. Then we can talk to the hypervisor that was selected. Maybe it needs to pull a virtual machine template to create a volume with. Maybe it needs to set up private networking, and all of this has to be done before the actual process, which materializes your virtual machine instance gets created. So that's in a sense the instance boots. And fair enough, in most people's mind, that's just a bit of glue, maybe a bit of Ansible, and off you go. In reality, it ends up being a bit more complex than this, and we use the opposite approach of saying, what do we want to do? What do we mean when we say orchestration? And the essence of orchestration for us is that we get an event that targets an entity which has potentially a current state. Out of that, we get a new state and potentially side effects to performs. And those side effects to performs, we basically map from an action name to an abstract syntax tree of sorts to perform. So that's, it can be seen as simple as that. And when you look at it from this perspective, it is a computer science. It is computer science domain, so development can be undertaken. We do this taking into account a few challenges. First, we need to ensure the formula you just saw can be applied, with concurrency, with some objectives in terms of resilience, taking into account that the side effects of the actions to perform could be long running. Materializing physical infrastructure is potentially longer, can run into seconds, minutes, for some of the operations, sometimes even longer. Obviously, we need to persist configuration and to have a regular convergence mechanism to ensure that we are in the state we expect to be in throughout the infrastructure. And for all of these reasons, so first, we are faced with a pure programming problem. We have a couple of key challenges around resilience, around persistence. We chose Clojure because we deemed it a great fit. So that's where we start from. And specifically around that issue, we built software around 4 axes. The axis of long-running side effects. How do we perform those across the infrastructure? Around observing the state of our systems, to be able to compare, expected state to observed state. Around configuration and around convergence. I'll start from the bottom of the pile with how we deal with long-running side effects and our approach to that. So just as I was describing a bit earlier, side effects affecting infrastructure can run for a long time. For instance, if we realize that we have a hotspot on the infrastructure, we may want to migrate a machine from a host to another. That process, which is transparent to the user, can take a while to materialize, because we need to, let's say, ship processes around, ship volumes around while we do it, and that can take a while. That being said, a lot of what we have to do needs very little in the way of control flow. So if I'm to take an abstract example, when we stop a virtual machine, we don't only send a command to the target hypervisor to say, please, destroy that process. potentially that virtual machine is part of a security group, and that security group is referenced somewhere else. So we also need to go and contact all of the other hypervisors which have VMs impacted by this stop to remove the IP of that VM from their firewall rules, because the security group is part of what we do. So the code to do that, if we were to write it in plain Clojure, would be extremely simple. Would roughly look like this. There's no particular how I say error handling here, but it could look something like this. We do have the issue of dealing with the observability of that thing. How do we know about its progress, and how do we deal with faults? So we could sprinkle try catch everywhere and log statements everywhere, which would basically help us deal with half of what we want to do in terms of failure handling. It would guard us against remote execution failures, but it wouldn't guard us against the process performing the side effect dying during the process, which could happen. And if we are to sprinkle left and right log statement to build a concrete report out of it, it also makes things a bit more complex than necessary. So we looked at the problem from a different angle and started to think about what we wanted for job execution, right? Because most of these jobs, the API that we want to expose is when you ask us to do one of these long things, you get back a job ID, and then you can come and look at whether it performs successfully or not. So in terms of our needs, we want the ability to do long-running tasks in parallel. I was describing that maybe we want to contact a number of hypervisors to remove firewall rules. That's typically something we probably want to do in parallel. Some things need to be executed in sequence to basically enable barriers of sorts, where we want to first do something in parallel, then wait for all of those to finish, and then go on to the next step. And we want basic rescue mechanisms, such as try catch finally. So the abstract syntax tree necessary to describe programs like these can be composed of very few things. So we have leaves, the actual actions to be performed, our sequential branches, our parallel branches, and our try rescue branches as well. So if we were to for instance, write a program that roughly looks like this, we end up with a tree that looks like this, with the A, B, C, D, E, F leaves being the actual actions to perform, and the do, par, do, try elements being the different element of control flow we support for our program of sorts. So starting from there, we also added in a couple of things we wanted to make sure could be done with whatever approach we took, which is that we wanted the ability to be able to restart execution from a previously known state of a program. We didn't want to tie the way we described the programs to any sort of execution context. So, like for instance, we didn't want to tie to a specific execution engine, so bake something on top of, I don't know, manifold or something else, but really to be independent from that, because our history showed that this is the sort of thing that you want to be able to quickly swap over time. And we also had this this issue where not all of our orchestrators exist at the same layer of our infrastructure. Some for instance, only have access to a very few things, such as a SQL database, and run outside of a cluster, while some others could have access to Kafka and different types of databases. So which opens up different options for building execution contexts for these programs. But the one thing we were sure of is that we wanted the same way of representing our control flows across our different orchestrators. And the current state of a program should be inspectable, which was our last requirement. So taking all of this into account and looking at squinting a bit at this abstract syntax tree, it quickly became evident that what we wanted looked a bit like continuation passing style, but should be free of the execution environment. So we tried to build a continuation passing style system which uses Eden to serialize the state of programs. What this design decision led to is forcing us to have the actual action execution be separate from the program description. So we built something which has a super small API, essentially exposes two signatures, one to build a job out of an AST, and one to restart a job. And what we mean by restart a job is that given a job and a list of results for previous actions, we get a new job. That's where the continuation passing style, I would say, heritage shows, and a list of potential new actions to perform. Then what's left to the consumer is providing the leaf execution functions. So if one of the leaves, for instance, is contact hypervisor with this command, that's up to the execution engine to provide. The default approach being a def method, where you implement the leaf action, where you implement the def method for the action name. And an execution engine. So the library itself bundles an in-process manifold executor, but you're likely to want to build another one on top of it. So if I come back to the instance stop job, with very few tiny modifications out of the previous function, instead of directly executing the job, I can build an AST for it and then hand over that AST to my execution engine, which essentially repeatedly calls restart on the job with the results of actions. And just as described previously, having all of this built as Eden also allowed us to quickly build visualizations on top of it, to be able to, first look at ASTs as we build them, but also to quickly investigate issues when APIs go sideways, instead of sifting through endless types of logs on different subsystems. So on this specific part, if we look back, building that library, which is actually open source, ended up being a relatively contained effort. It provides us with two levels of indirection, which is quite convenient. When we change the meaning of what stopping an instance is, we can modify the AST that's built out of it. And we can also modify what we mean for each action, right? Because then the dispatcher for each action type can also evolve over time. So we have these two layers to evolve over time. Using Eden and so data to represent the AST gave us these nice hooks to build visualizations on top of the progress. Ended up being quite convenient, and the pluggable execution engine aspect of the library makes for a convenient way to evolve the resilience and the concurrency, the aspects of that of side effect producing and handling without touching the core of our orchestrators over time. So we started with manifold, and we evolved towards a SQL-based approach over time. And roughly that's that part now is at the heart of all of the side effects that we produce, and also ended up socially being interesting because we also blended the way we build our operator runbooks to be based off of Ablauf ASTs, which means that a single way to a single representation of workflows is used both to inside the software we build, orchestrators, but also for operator actions. Let's say if I want to retire a hypervisor, I need to migrate left and right all of its virtual machine, but that's something that an operator may decide to do, right? So there's a convenient API call to do this, which then materializes this as an Ablauf AST with a couple of how would I say simple primitives we added to quickly build scenarios. The second aspect of our orchestration platform deals with observing state. And here, the salient point here is that we need a state observing mechanism for two key reasons. The first is that we want our allocation decisions to rely on fresh data, right? If your notion of how used each of the object storage partitions are dates from 2 hours back, potentially you're overloading disks on nodes that are currently being underwater. And we also want low latency propagation of state changes to react to infrastructure being modified live. Right. So these two aspects are led us to build a state observing machine. So a simplified view of what we want is here it's hypervisor represented because I'm focusing a lot of what I do today on the virtual machine instance ecosystem, but this applies to most of what we do in object storage and for the other orchestrators as well. But so we want to emit state data as a stream and to materialize, and build a materialized view out of that stream in a store that can provide low latency lookups from any types of orchestrators. And a second aspect is that when entities get change, we also want to build a secondary stream off of it, which notifies the appropriate orchestrator that an entity has seen a change, so that a convergence run can be triggered. On the actual materialized view, what we want looks a lot like the typical NoSQL database these days, as in we want fast key value access with a bit of flexibility into the dimensions we want to look up. So we may want to find all VMs which are part of a specific instance pool. We potentially want to find network load balancers that are tied to a Kubernetes cluster we manage, or things like these. And the lookup mechanism should be as simple as possible. As I was showing earlier, we need to emit state, and that's part of what we don't do in Clojure actually at Exoscale. So we built a bit of a tower of languages at Exoscale, where the default choice is Clojure. Everything that runs centrally is done in Clojure. We also do the user experience part in Clojure as well, but whatever runs close to the workload, so on actual hypervisors, on storage nodes, on our storage chassis, tends to be either Golang by default now, or when necessary C, or an even smaller language. But I would say the vast majority is now Golang. And so to implement what you saw, well, here we went the canonical Clojure way, at least looking at the other Clojure users we know about. This seems to be a very common approach. The stream ends up in Kafka, and we build materialized views with Kafka streams. And I won't spend too much time on that specific part of what we do, because I think that that's again the typical Clojure projects. For us, it was extremely convenient. We were able to capitalize on the Kafka streams knowledge we already have, because it's also heavily used for billing purposes and account change reactions as well at Exoscale. That being said, it's in the realm of things people usually do with Clojure, I would say. The third aspect, though, that we have is our configuration persistent engine, and here it's a bit. I wanted to spend a bit of time on it just to defend a bit the choice, because we end up with entities having a tree shape mostly. We want as much flexibility as possible for queries, so basically to build a part of the tree as we query data, but we want full control of mutation as much as possible. So the obvious choice for this is Datomic, right? You get the pool syntax, an easy way to perform mutations, plus that being said, it wasn't an obvious choice for us for a couple of reasons. First, the actual infrastructure footprint of Datomic is non-negligible, and this being part of our orchestration platform, even though a lot of Exoscale runs on Exoscale, the actual virtual machine instance orchestrator does not. So it has to have a relatively small dependency profile. Ideally, not much more than a SQL database. And the second part is that we don't deal with an amount of with a cardinality that's completely crazy. So essentially, here we can weather the having a standard SQL database to do the job with no issue, and the join ability of SQL makes for a nice way to build trees as well. The only problem is that the trees that you get out, they're not nicely shaped trees that you would get with something that supports pool syntax. So yeah, that's a bit what entities can look like, and the types of the relationship we can have over the data we host. And as you can expect, I mean, when I say low, the kernelability, it's like it's not in the millions for virtual machine instances for us, which is so basically there's a large amount of room to grow as far as we're concerned. So knowing this, we went in with saying that we wanted something that relied as much as possible on standard libraries in the Clojure ecosystem, because that part is relatively well standardized now in the Clojure ecosystem. We wanted the Clojure spec integration and what you'd expect from something that works with SQL correlation support, as well as transaction support. So again, we went in with NextJDBC and HoneySQL, spare some more on coax at the end. And that's what we mean when we say we want integration with Clojure specs. So the library we built allows us to infer the schema of a specific entity from a spec, and to out of the box start querying it. And as you can see down below, the query language we went with looks a lot like the full syntax of Datomic, because that's actually what we wanted to be able to use. So as soon as a relation is inserted, we can build a tree as deep as we want, which maps, which creates the corresponding SQL query and allows us to have the flexibility we want with our query mechanism. Then the rest is more like the standard bread and butter. There's ways to add the standard mutations, and in many cases, you may actually want to use a specifically named mutation which produces SQL code. So for mutations, we don't enforce any specific opinions. And of course, transaction support, as well as listeners to enable CQRS style workflows, where after a change in the database within the transaction, you get notified of a change so that you can perform additional actions if need be. And yeah, and that's it for, actually, it's only mentioned at the end of the slide, but that's also a library we open sourced called SQL, which is a thin layer on top of NextJDBC and HoneySQL. And so the last element is, how do we tie all of these parts together, right? So we have this library that helps us persist our configuration. We have a way to observe state. We have a way to perform side effects. How do we tie everything together? And how do we trigger side effects when necessary? So just as a quick refresher, only 2 ways roughly to generate to have something being generated. The first is through a user action. So I want a new instance. I contact the API. The new entity gets persisted in a SQL database. Then a side effect is produced, and we get back to the initial picture where we had allocation and the different side effects needing to be performed. And the other case is there's a state refresh. So potentially the health check for one of the target members of a network load balancer. A health check reports down, then the state gets updated. After the update, the orchestrator is contacted. Again, a convergence run happens. And here the convergence run is in both cases noted as FSM run, which is a bit of a tell into how we do these things. So we converge by doing this. We only serialize our target state on the entity, and then we apply a finite state machine run on top of the expected state and the event to decide what action to take. And here again, we wrote a small library to build these finite state machines. which is also available as open source. The specific, how would I say, types of finite state machines we use are called Moore machines, and they take a state and an event and produce a new state and the action to take, potentially. So in a sense, with all of this, we get back to this original picture. At the core, that's what we do. Where we apply very few things. And I think that's the key part here, is that these two things that we do, which are at the heart of all of our orchestrators, using these libraries help us, one, remain extremely small. There's not that much code to handle for instance, a managed Kubernetes orchestrator, which is not necessarily a small project typically. And it also allows us to build tests in isolation. For instance, do we produce the correct data, the correct AST for a specific type of side effect? Or are all of our state transitions, our finite state machines actually finite? Or do we have weird dangly states in some cases? Those are the things that we can easily test without having to build integration testing platforms, which are hard to manage and slow running. That's not to say that we don't have those, but we can build tests that exercise all of the corner cases of an orchestrator without having to actually contact actual infrastructure. And the last part is that having baked this Clojure spec support, like this inference from Clojure spec in SQL and in a couple of other places, we can start from our entity descriptions that are built off of Clojure spec and have that permeate to all of our systems. I'll probably publish these slides, but yeah, we have a bunch of libraries, as I was describing, to support all of this. One which is still pending, an open source release, which is at the heart of all of how we build our Open API compliant APIs. But the rest is already available and ready to be used. And yeah, those are supposed to be parting words, but I actually mentioned them in introduction, I think. So that promise, which is I mean, at least for us, the promise of having Clojure as a tool to compose focused libraries is really something that delivered for us. And really Clojure spec ended up providing the safety net and the building block we really needed to be able to structure our code bases together. Yeah, and I guess a third parting word is that it's the first time I give this specific talk and that I describe our orchestration ecosystem. So also happy to take feedback on what ended up not being super clear, if anything, which I guess there is. And that's it. That's what I have for tonight. Thanks, everyone.